Good morning. Welcome to my presentation. My name is Binwei. I'm from Walmart Global Technology. So today my topic is semantic label representation with application on multimodal product categorization. I joined Walmart Technology, Global Technology, as part of an acquisition back in 2014. So I've been in Walmart for 8 years. My area of interest is in computer vision, multimodal modeling, and its application in e-commerce use cases. So let me motivate today's presentation first. We all agree deep learning has come a long way, and then when it's applied to image classification and other type of machine learning, the performance has been amazing. Right? Oftentimes you can frame the performance of a classification model through this lens of confusion matrix. Right? So if you can picture a perfect classifier in your mind, there's no confusion there. By the way, I don't have a picture of the perfect classifier on this slide, but I trust you can imagine in your mind. Basically, the confusion matrix for that classifier would have only non-zero numbers on the diagonal, right? Wouldn't that be great if we can all just get perfect classifier every single time? But the question to ask here is not to how to build a perfect classifier every single time, but rather most cases in the practical sense, perfect classifier is not realistic, or even can be a misguided goal, right? So the part that it is not realistic, I think we all have some experience with it, right? It's acceptable. But what about the part of that potentially being a misguided goal, right? So if you arrange the classes that are related to each other based on your prior knowledge of class structure, class hierarchy, whatever you call it, if you arrange classes that are related to each other next to each other along the rows and columns of the confusion matrix, if the model does a decent job, what you should see is this block diagonal pattern. What it means is the classes that are related to each other, the model could be confused with them, but it should never confuse classes that are not related to each other, right? So the industry has been fixated on training a perfect classifier. Unfortunately, what we end up building oftentimes is a model that shows a pattern on the lower side there, right? So the model is not only confused with related classes, but also making really bad mistakes when it misclassifies things. So with this talk, what I'm trying to do is kind of reset the goal and offer one of the probably many possible solutions that can lead to the sparse block diagonal confusion matrix pattern. So on this chart, I'm showing the state-of-the-art model for image classification on ImageNet. This trend has been going up and up, right? But it probably won't go to 100%, right? So this paper captures the one problem of this state-of-the-art models really, really well. I'm not going to read the whole thing, but basically it says by just focusing on this performance measure, typically top one accuracy, when you treat all classes other than the ground truth as equally wrong, this typically leads to a situation where you're improving the accuracy, but when you do make mistakes, the mistakes are still pretty bad, right? So so I work in e-commerce domain. We deal with a lot of classification models, and they all suffer from this problem. So we have been improving the performance, but when we have misclassification issues, when you look at the mistakes, it's often far off the true class. What I'm hoping to do today first is to give you a context using the product categorization use case, where we happen to use multimodal features And then we'll offer a solution through the lens of semantic label representation. And in the end, I'm going to share some experimental results. Yeah? Okay, so let's talk about this product categorization use case. Also, we're using multimodal modeling. So product categorization is basically taking each item from the catalog and categorize it into one of few thousands of product types. It's a perfect use case because it has a huge taxonomy. The class relationship is relatively complicated. And there are also popular classes with lots of items. There are minor classes, minority classes with fewer. So there's like a big imbalance problem also, right? So multimodal feature is not essential to this discussion around semantic label representation, but by looking at this few examples on the slide, you can agree when the model has access to both the title and image of a product, it has a much better chance of predicting the right product category than if you give it only the image or title, right? So multimodal feature does help. And accurate product categorization is fundamental for e-commerce operation. It's not just important for revenue growth, but also critical for a positive customer experience. We happen to use CLIP. So for the sake of this conversation, OpenAI's CLIP, it's just sufficient to know that it's a contrastive language image pre-training network. It's trained on 400 million pairs of image and caption. So the network is actually constructed in such a way it has a text encoder and an image encoder. And the loss function is a contrastive loss. So its benefit is like unifying the two embedding space. And it's a pretty simple network, but because the large amount of data and the way it's using the contrastive loss, it's pretty effective. The way we use it is we take the CLIP encoders, so basically pre-trained CLIP encoder networks. We then generate image and text embeddings from the encoder. We fuse it using attention layer, and then we train a fine-tuning network. I want to emphasize that the fact that we're using multimodal encoders, we fuse them, this is tangential to the discussion again. So it's not inherent for how you represent the models, how you use semantic information. But to compare with this baseline model, it's important that we freeze the CLIP encoder, right? So we only train the fine-tuning layer, which consists of the attention matrix and multi-level perceptron. And we also use focal loss for the multi-class loss to address for the imbalanced data. Okay, so that's kind of the context for the use case. Now this is the core of the discussion. So we're going to talk about semantic label representation. Okay, so we've been talking about labels, right? And the previous speaker also talked about label can be ambiguous, right? It's human interpretable. So labels are human-generated signals, right? They're information dense. They're inherently ambiguous. Maybe it helps to kind of look at a few examples here. I have 3 classes: cowboy boots, rain boots, and T-shirts. 2 of the classes are relatively closer to each other. On this slide, on the left, I'm showing you 2 encodings of the label representation. So by looking at the one hot encoding, you wouldn't be able to tell whether A and B are cowboy boots and rain boots. B and C are relatively far apart, right? So you wouldn't be able to tell which classes are related to each other, which are not, right? But one hot encoding has been a convenient choice when it comes to supervised classification model, right? The supervised classification training typically leverages one-hot encoding with the help of cross-entropy loss to basically maximize the probability assigned to the ground truth class. Right? So if you think about it, right, every class here is essentially treated as an anonymous class, which has nothing to do with any other class. Right? So that's a kind of the intrinsic problem here. It ignores the similarity between the classes. As a result of that, when the model fails to distinguish between related class, let's say between B, A and B, right, it's punished to the same exact degree as when it fails to distinguish between two unrelated classes, let's say B and C, right? So, and the paper I'm quoting here points out that one-hot encoding typically results in overfitting of the model. And if the model learns to assign full probability to the ground truth label for each training sample, it is not guaranteed to generalize. Right? So the previous speaker also talked about overfitting can be one of the pitfalls. So the same paper, so this paper basically really summarizes the fundamental flaw of semantic agnostic approaches. Right? So the same paper actually offers label smoothing or uniform label smoothing as a solution to that problem. So let me take some time to explain what label smoothing is. So instead of one-hot encoding, think about each class as a probability distribution over all the classes. So instead of assigning one, it's like a binary probability to each class, you assign a less than one weight to the true class and distribute the remaining weights to all the other classes equally. Right? So it's a pretty simple idea, but surprisingly, when you apply to model training this way, it shows tremendous improvement for not only generalization and also performance of the model, like calibration of the model performance. Okay, so those are the kind of the baseline existing approaches. Now I'm gonna take the next couple slides to talk about semantic label smoothing, which is built on top of the idea of label smoothing. So essentially what we're assuming is you have some notion of class relationship. And furthermore, you have some way to quantify the semantic distances between the classes, whether it's in the form of pairwise similarity metric or pairwise distance metric. The whole idea is if you can encode that information and basically embody that information in some kind of probability distribution of weights over all the classes for your label representation, then you could basically take advantage of the prior knowledge you already have, right? You don't just throw away all this knowledge you have about the semantic relationship between the classes. So let's just take the example of the three classes A, B, and C. You can look at the sort of the leftmost column there. So if let's say you have the pairwise similarity metric between each pair, right? And then you can frame that into a similarity matrix to represent the relationship between each pair. If you can transform that into a semantic affinity matrix, whereby you preserve the distance between each pair, in this probability distribution weights, then if you can compare that with a uniform label smoothing, where basically you also have a distribution, but essentially you are still ignoring the fact that classes, some of them are related to each other, closer to each other than others, right? So it is the distribution, but you are actually encoding the actual distances between the classes. maybe that's not very clear. It's actually not a new idea. So if you actually frame this on this slide in a slightly different way, you probably see, oh, actually we already use it in some other environment, right? So think about knowledge distillation, right? You take the teacher model that give you logits, you soften it by basically apply a softmax with temperature to arrive at some kind of a soft targets before you use it for the distill that knowledge to the student. Think about that, and then if you can actually take the adjacency matrix and in the same fashion apply the softmax like transformation, whereby you actually arrive at a soft target like distribution, and the probability already sum up to 1, right? If you have that kind of construction, and then what that gives you is you can now take that distribution, basically the way you represent the labels, and calculate a KL divergence loss. So what that does is basically take the model's logits and enforce that the logits represent the distribution as what you want in the label, in the target label, right? So you're taking into account that the classes are related to each other. So when it comes to actually how we quantify the distances between the classes in this example of categorization of product types, we happen to use CLIP, right? And CLIP is a powerful language model, right? So we actually can take the CLIP encoder, get the embeddings for the product category names, right? It's a rain boot, it's a cowboy boot, it's a t-shirt. We actually take the names literally and get the embeddings for those product category names, and then we can compute the cosine similarity score, right? That's kind of our basis. We use that to construct this soft targets. And in practical sense, we actually cut it off at top 20 nearest neighbors, because we observed that beyond certain number of nearest neighbors, the similarity ranking becomes very noisy, and you actually don't care about those things. 20 is somewhat random. It's really based on your use case. So on the right, I'm showing from the baseline model, what we do is we have this KL loss as a secondary loss, right? So we basically combine the two losses during the training, right? And then the temperature parameter and then the fraction that we give to the KL loss, they're all trainable parameters. Okay, so it's all fine. Just do a time check. So how does it really work, right? I mean, when a rubber meets the road, what does this mean, right? So we did an experiment, and we basically focused on 4 concrete implementation, right? Let me just take you through the methods here. So one-hot encoding is our baseline model. Number 2, we basically take the uniform label smoothing idea, and in this case, we assign 0.9 to the true class, and we distribute 0.1, over the rest of the classes equally. And then third method, we start to incorporate the semantic information. So now we calculate the distances, but we cut off at top 20. But we say, okay, well, we don't really know exactly how they should be ranked. So we just give the top 20 equal weights, right? So we set all the other classes to 0 and use that weights to represent the labels. The last one, we actually literally take the weights, takes the cosine similarity score for the top 20, and then calculate the weights accordingly, right? So table 1 shows how much improvement we get for the 3 methods against the baseline model, right? You can see that for the top 1 and top 5 accuracy, they all have large improvements. The best model is the method number 3. So this is uniform label smoothing. It's still uniform, but we only do the top 20 nearest neighbors. And interestingly, even the basic uniform label smoothing method number 2 comes second. Okay. But that's not actually all we care, right? Yeah, if we can somehow squeeze a little bit out of the poems, out of this, we're happy. But like we set out to say we want to make better mistakes. When the model misses a mark, we want the prediction to be close to what the true class is. And the measure of that is your top 20 nearest neighbor, right? So this next metric we do is to basically take the top predictions of the model for each sample, compare how many of them actually land in that first top 20 nearest neighbor, right? I know it might be a little bit confusing if you look, but if you only look at the last two rows, the second last row shows what is the percentage of samples for which the model predicted, the top 5 prediction, and then all top 5 prediction by the model fall within that top 20 nearest neighbors. So the baseline model, only 1.55% of the samples satisfy that requirement, right? What that translates to is, on average, only 2 out of the top 5 predictions from that baseline model will be in that top 20 nearest neighbor. So you're not surprised anymore when it misses the top 1 prediction. More often than not, it actually is not even close to what the true class is, right? Compared to the best model 4, where 57.1% of the time of the samples, all top 5 predictions fall within that top 20, right? So you can see the tremendous difference there. Right? You can kind of look at the 4 and say, most of the time, 4 out of 5, they're within that top 20. So even if the top 1 is mismatched, they're not too far off. That's actually all I have done in this project. So the takeaway here is we talked about the semantic aware approach number 4, right? This is when you have the quantifiable similarity metric between the classes, you can actually use that to improve your performance. And then in production, what we do is we actually combine this model with another model that is just purely optimizing for top 1 accuracy. So when you do it this way, you strike a balance between the accuracy and the semantic similarity of the top predictions. Okay? But I think also it's probably it's much easier to try this semantic awareness approach number 3, where you basically say, I don't know how to quantify the relationship, right? I don't know how to rank the classes in terms of closeness in absolute order, but I do have some notion which classes are kind of bundled together, right? And the top k nearest neighbors is all you need, and k can be 20, can be something else in your use case, and it also doesn't have to be the same for all the classes, right? If you think about the ImageNet classes, right, there are so many birds, so many dogs, they have relationship with each other, so you can decide like how many close neighbors you want to model with this approach. And this will actually give you a leverage when you have this situation. So both are recommended, but you can kind of decide what to try, at least what to try first, right? Since I have a little bit more time, so I'm going to offer some intuition. So before we go to the questions. So if you think about it, right, what this loss function allows you to do is first, you can inject prior knowledge, right? Number 2, the loss is reduced the most when the model learns to differentiate classes that are not related to each other, right? So if the model makes a mistake that confuse unrelated classes, if you think about it, because the way you set up the weights, it's going to be punished more. So we'll try to learn to differentiate those unrelated classes. So that's 1. 2, when your labels are very noisy, right, you have mislabels in your training data, this approach is more tolerant, right? Because if you confuse rainbow boots and cowboy boots, right? Because their representation are actually pretty close. So the model is not like super sensitive to like, oh, you have one label that is wrong, right? Third, when you have imbalanced data, right? When you have like lots of, let's say, cowboy boots, fewer rain boots, the model actually tries to, it will basically learn in a sense like it's pulling all the knowledge together. So the imbalance ratio is not as severe in terms of impacting your performance. Yeah, so I think that's hopefully something concrete and practical you can try. I have learned a lot from MLconf in previous years. It just feels so good to come back and give back to the community. Yeah. Now I'm ready for questions if you have any.
Awesome, thank you. Questions, please. We have a few over here, we'll get to you.
Yes, have you considered using regression task rather than just like assigning this probability distribution to the different classes that you have?
Regression.
So you kind of like do like some kind of like numeric score for each class rather than like for each product rather than just like using a fixed one-shot class?
So let me just clarify. So are you talking about when I come up with the label distribution weights, or are you talking about actually using the soft target but doing some kind of regression as a loss function?
Using a numerical value to like denote the task, right? To do the class.
Okay, to assign the weights using some kind of regression.
Yeah.
I think you could think of like some kind of sample data that if you have some annotator that can label like this like these are close together, you have some kind of range. I think you can. So you don't have to use the embedding approach to come up with the weights. Clustering is something that I can think of. You can do. So you can sort of measure like this 20 classes are close together. They have a centroid, and then somehow you can measure the distance between them. So that.
Yeah, I think that could be some of the answer. Thank you.
Yeah, first, congratulations on the great talk. Awesome. So I have like two questions that are very related. So one is, you are pre-encoding like knowledge that you had from the clip embeddings for the labels. So are you using just the label text, or are you using the entire, so you probably have a category tree. So are you using the entire path leading to the label for the pre-training encodings?
That's a great question, yeah. So you can try many different approaches, because when you actually retrain this, right, all you need to do is really just a simple pickle file where you have the weights assigned, and then you can just inject it. So what we did try is one, we use different prompts. So you don't use a raw category name. You use, I mean, Clip has this well-known ImageNet style templates, right? You can say this is the photo op. If you take that, chances are you will improve it, but this is because it's e-commerce catalog. Maybe it doesn't work some other. And the other thing you're offering is like this breadcrumb kind of hierarchy path, right? It may or may not help, because if you think about it, many of the product types, they belong to multiple passes. Like they can show up in different hierarchy, right? So it's not a one-to-one kind of parent-child relationship.
Yeah, and related to that, it might be a good idea to explore using the navigation patterns of users on the site to also add like extra information on the categories, because like the searches and the navigation patterns are usually, they're trying to find a specific product, so that might be extra information that could be useful for the pre-training.
That's very interesting. So I think you're saying take the queries that basically take the query understanding. Right? Some of the queries, basically they imply certain product types. And if you can aggregate those queries and say, where are their centroids in some kind of space, and then I think you can use that as a proxy to where that category is in the embedding space. And I'll probably try that. Yeah. Okay.
Hi, my question is, does this technique really help you with class imbalance? And
Yeah. So
what was your observation?
Yeah. So that wasn't the intention in the beginning, right? We have huge imbalance. To give you a sense, like we have millions of T-shirts. We only have like a handful of, let's say, iPhones, right? iPhone items. So what I noticed is if you don't use focal loss, if you just use the plain vanilla cross entropy loss, that doesn't work. Like, the accuracy shows up like, pretty good, but when you look at each categories, some of them have 0 recalls. So use focal loss is our first line of defense. And this helps, as I said, it depends on how you construct your training set. So during your training set construction, you are consciously, some classes are more popular, so you try to mitigate that. But when you have this class hierarchy, for apparel, for different boots and rugs, we have lots of those. I noticed they do slightly help because again, the model is learning them as a whole, because their representations are very close. Yeah, so I think it's a secondary fact. It's not the primary goal.
Yeah, seems like it. Thank you.
Wonderful session, Binwei. Thank you so much.
Thank you. Thank you, guys.